Hello everyone, welcome back. Hope you had a good weekend. So I sort of stopped in the middle of, the last part of the proof of this theorem we were doing. Let me just briefly recall what we were doing. We were trying to complete a measure space, yeah? So you had in general, we realized that it is not necessary for a set of measures 0 to have every subset measurable, but that is what we would like to happen. So we were trying to complete, given a measure space like this, XMU, we defined this M star in the following way, and then we defined an extension of the measure mu to this M star, and we wanted to show that M star, just 1 minute, M star is a sigma algebra and mu bar is a measure on M. So we did the first part completely. We did show that M star is a sigma algebra, and we were just starting to show that mu bar, where mu bar is defined in this way, and A is the subset of E. A and B are the subset and superset of E that we were looking at, squashing E. So mu bar we defined this way, and I just shown that mu bar is well defined. So we still have to check that mu bars is countably additive, and there is something in M star which has finite measure. That's all right. So there must exist, should we write some S? So mu S is finite, and since this M must sit inside M star, because remember, mu bar S is just mu S for elements of, they agree. We said we just take A and B to be the set itself for elements in M. Okay? Are you with me till here, everyone? Shall I proceed?
Yes, ma'am.
So now we try to prove that this mu bar is countably additive. So as we have already done before, we take a family EI of sets sitting inside M star, and then you will have the corresponding AIs and BIs with AI, BI in M. And do we need one more condition, or is this enough?
Yes, we need.
You need this. Yes. And now what do I want to show? That mu bar of union EIs is summation of, we want to show this. Yes. Mu bar here. Okay. And if you recall, we have worked with this before. So for the, if we write as union EIs, we showed that this E was in M, because if we define all these sets, then A is contained in E. We saw this before. E itself is in M star. And now, by definition, what is mu bar of E? It's simply mu of A. That's how we define, remember? Yeah. And that's mu of union AIs And mu itself is countably additive. So we have and each mu AI is nothing but mu bar of EIs. Right?
Yes, ma'am.
Therefore, what have we shown? So do you think we have finished proving this theorem?
Yes, ma'am.
Okay, but what was the purpose of proving this?
Is a measure. Mu bar is a measure on M star.
Okay, we did it, but before that we had this discussion about why we were doing this theorem. We wanted the property that if E belongs to M star and mu bar E is 0, then if N is also sitting in E, N should belong to M star. This was a property which might be missing in any usual measure space measure that we take, and we had some trivial examples we looked at. Okay, so that was the purpose of extending this measures from M to M star and mu to mu bar. So do we have that now? In this construction, can you see that? Just referring to what we have just finished, we should have this property, right? Otherwise, there's no point. Why would we just extend the measure? Okay, so this is what we should prove. So let's assume the same thing. I will write M star mu bar E is 0. Can anybody think why this would happen? Again, there exists, because E is in M star, so there are these sets. A is contained in E is contained in B, mu. Okay, and we want to show that N is in M star. Why should it be? That means I have to find some A sub N and a B sub N such that means I need to find A N where these two are in M, AN and BN are in M, and mu of BN minus AN should be 0. This is what I have to do, right? Any ideas what we should do?
We can take AN to be A and BN to be B.
But how will that ensure for the same thing for N?
Because N is a subset of E.
Huh?
Because N is a subset of E.
A is a subset of E and N is another subset of E. But there is no guarantee that A will be a subset of N, right?
Oh, yes, yes.
So let's see. What if I write N? We can always write N as, this is possible, right? And this set, of course, is contained in A because En is contained in E and E is contained in B. Okay, that's fine. And what can you say about, and A union B minus A will be in M, isn't it? Because A is and B is. Further, what can you say about mu of what will this be? In fact, these are disjoint sets.
Mu of A.
This? Okay.
Is mu of A.
Mu bar of E, you mean? Yes? Remember, mu bar of
mu
E
bar of E.
and mu of B minus A is 0. Yeah, so, and that's 0. Okay. So now I have one set which is sitting here, which is n is sitting inside this set, and mu of this set is 0. So now the choice of this an and bn suggests itself. What should my bn be? That is clear. What should bn be?
A union B, difference A.
Right? Then it's clear.
Yes.
This is the definition of M star. That's what we required. And of course, once you know that n is an M star, mu bar n, which is going to be less than, will be 0. Okay. And this property of mu bar is called completeness. Okay. So let me define, this was the purpose of doing this theorem. And here is the definition. So a measure mu on xm, a measure space, is said to be complete if for every E with mu E equal to 0, n contained in E implies n must be in this measure. Okay, and mu bar in the previous theorem is what? Is complete. That's what we showed. That's what we have just shown. Okay, is that clear? Okay. Okay, so this brings us to the end of the theorem we had started last time, and I'm going to stop sharing and switch my board notes. Okay, just 1 minute. Can you see my lecture 3 written here now? Yes?
Yes.
Okay. So now what we have done till now, we have shown that we have said what we mean by a set of measure 0. Sorry, what it means to say almost everywhere. Something has a property almost everywhere. So with that in mind, and remembering that so far, what kind of functions have you been looking at? We say f is from x to c 0 or 0 infinity on. But f is always defined on all of x. So for example, when we looked at the Libate dominated convergence theorem, in the hypothesis, you had f from x to c. You wanted this domination by gx for all x in x. And we wanted for all x belonging to. Okay. But now with this notion of almost everywhere, we can make these conditions and even this definition of measurable a little, or expand this definition, so to say, and make these two conditions, for example, less stringent. Okay, so for one, we may not need f to be defined on all of x. Okay, because after all, the whole idea of doing this exercise of constructing a measure, we want to have good definition of integral. Okay, and just we have just seen in the last lecture that the if two functions are equal almost everywhere, the integrals are equal. Okay, so with that in mind, we expand slightly what we mean by measurable functions now. Okay, so now we will say a function f. So x m mu is given to us as always. So now we say a function f defined on a set E will be called measurable if the following two conditions happen. So this one is what we have done already. So this is measurable for every open set V, of course contained in Y, if we are saying is from E to Y. Okay, Y is a topological space, and outside of E, we don't care, provided 2 happens. That is, the measure of E complement is 0. So this is the complement of E in X. So now we are just concentrating on E. And in fact, we can define F to be maybe 0 on EC. So we can extend F to all of X by setting okay, and then also you will get a measurable function. In fact, if we take mu to be complete, all life becomes much easier. You know, we don't need we don't need to say what f is outside EC. We are just going to work with on E and just forget about the complement. Okay, and the integral of f over any set, say A in M, will be independent of the definition of f on E complement. Okay, so it doesn't really matter. And in fact, like I told you these things about Libate dominated convergence theorem, we can modify it slightly and say maybe here make these changes also. So such instances you will see several times. I'm going to prove one result which actually just illustrates this fact. Okay, that what is happening outside of a set on a set of measures 0 will not come into the picture for our main results. Okay, so this is the objective of doing this result here now. It can be thought of as a corollary to Libate dominated convergence theorem, or you could just look at it and derive, say that from here we can write off the Libate dominated convergence theorem in the almost everywhere version. So let's see. So suppose Fn is a sequence of complex measurable functions defined almost everywhere on X. Okay, so this means again that there is a set, say Sn. Fn is defined on Sn, and the measure of mu of Sn complement is 0. So this condition is true. Then converges for almost all X. So now we are not saying for all X belonging to X. The function f is in L1 mu, and the integral okay. So here, what will you see? That you have this condition, convergence is almost everywhere. The functions are defined almost everywhere, and yet your integral here, condition 3, we are all okay. Because of course, sets of measure 0 play no role when we are talking about the integral over all of X. Okay, so let's start proving this. And after I have proven this, I will ask you to take as homework to write the proof of the Libate dominated convergence theorem with an almost everywhere version. I will write down the statement for you, but you should definitely try and write out a proof. So let Sn be the set on which Fn is defined. Then this is 0. Let S be intersection of all of Sn's. And let's see all okay? Shall I go ahead?
Yes, ma'am.
Okay, so now since you didn't ask me this question, I'm going to ask you and you will have to give me the answer. Why, if I'm writing S like this, why should S not be empty? See, because if I just left it here, it's fine. But now I'm defining phi x to be this for all x in S. So you should always ask, what if this is an empty set? So now I will not give you an answer. You have to think. And I think it will be clear in the next 2 steps if you are paying attention. But I will ask you to give me this as, if not by the end of the lecture, the next lecture. Okay? So now I have taken this intersection, which is for some reason not empty, and I write phi x as this limit, the sum for all x in this intersection. So of course, if x is in S, that means each of these f and x is defined, right? So this makes sense. Now, what can you say about because
S complement is union of n from 1 to infinity Sn complement.
exactly
And measure of Sn complement is 0. S will be, measure of S complement will be sigma mu of Sn complement, that is 0.
and each of these has measure 0.
So summation is also 0.
Did you say the measure of this is summation?
It's less than
each?
equal to.
It's less than equal to. Yes. It's not less. Yes, exactly. Less than equal
but
to.
anyway, since it is less than or equal to, it must be 0.
Yes, and we are working with non-negative measures. Okay. Later on, if you pursue this line, you will also come up with signed measures. Okay. So here we remember mu is from m to 0 infinity. We are talking about positive, non-negative measures. So things work in certain ways. Okay, now you recall this result. So what do we have? We have a phi here. And
mu of S complement is equal to 0. So is it why S not equal to 5? Because if S is empty, then mu of S complement is not.
Exactly. So I have yes, good. Yes. Now just recall this theorem. This you would have done in the first part of this course. So see, what have I done? Basically, what I've done is I have moved from Sns to S, and we know that this function phi is defined everywhere on S. So if my fn's were defined on all of x, this we would have not used this step. We would have just said, let phi x be this, okay? Right? But here, so this is a usual thing you will do when things are defined almost everywhere. You will move to to a subset where the function is defined or whatever you're trying to study is defined. And outside that, there is a set of, the measure is 0. Okay? Okay, now we know this. And if you write gx to be summation gnx, so remember this was of course for all x's we were talking about, then yes, do you remember doing something like this?
Yes, ma'am.
Yeah, okay. So now, by this result and hypothesis 1, what was hypothesis 1? This integral is finite. The sum of these integrals is finite. So we have do you agree? Yes. Remember, phi we defined like this. So now instead of in my the theorem that I am asking you to recall from the first part, in that my g I am taking as phi. Okay. And gn's are just these mod fn's. So everything is non-negative. And instead of applying things on X right now, I'm putting things on S. Of course, in my hypothesis 1, you have this is finite, but that means, of course, on a subset, this is going to be finite. And anyway, on measure 0, this will not matter. We have seen this, right? If you write integral x, say h d mu, and because this measure is 0, this will not come. We have seen this. Last lecture, we saw this, okay? And even if you didn't have that, this is a non-negative function. So on a smaller set, the integral has to be less than on all of x. Okay? So now let me set E to be till now we have not said phi x cannot be infinity. It is just a sum of non-negative numbers. Recall again, phi x is this. It could as well be infinity. Now we are saying only consider those elements of S for which phi x is finite. Then what can you say about E complement? Okay, so I'm doing this little computation for you. So to see why measure of E complement should be 0. Okay. Okay. Now this set, what do you know about the measure of this set? Can anybody say?
0.
Exactly. Why?
Because mu of S complement is 0 and E complement intersection S complement is the subset of S complement.
Exactly. So we are left with this. Now, if mu of E complement intersection S is not 0, which means then it is strictly positive, since what is this set? What will this set be? Remember, E is all the x's in S as that phi x is less than infinity. And what is the only possibility for this?
Equal to infinity.
Is infinity. Exactly. So can you see the contradiction? See, 4 is saying this integral over phi is finite. Now, if this set, so, you can write this set. If
Its
this
measure
set,
must be 0.
exactly, in view of 4, we will need to have contradiction, right?
Yes, ma'am.
Therefore,
Mu of E complement intersection S is 0.
now, because of whatever this thing I should call it, 5. Okay. So, what does that mean? Phi is so this means, okay, just let's So what have we done? Where E is the set. Okay, let's leave this for a minute and go back to phi x. What was phi x? We defined it to be summation mod f in x and on x belonging to S. E is, okay, we have already written what E is. So now for every x in E, series, look at here. Let me call this series 2. See, phi is summation n going from 1 to infinity mod f n x. Yeah. And fx we have without the modulus. So if I know that phi x is convergent or phi x is less than infinity, that is saying the series in 2 is absolutely convergent, isn't it? Okay. Is that okay?
Yes.
So I can say that for every x in E, this series in 2, what was that series? Just simply
Fn of x from 1 to infinity.
Converges
Absolutely.
absolutely.
Almost everywhere.
I have said for every x in E, the series converging absolutely.
Okay.
Yes, because we know that phi x is finite. Phi x is not finite for every x in S. We haven't shown that. We have shown that phi x is finite for every x in E. Okay. And mod fx will be less than mod f in x. And that's right. Therefore, right? Is that okay?
Yes, ma'am.
So what, because remember we have to show that f is in L1. That was the, so this is the disadvantage of not having a big board in front of us to keep going back and forth. So this converges for almost all x in X that we have already done now, because you have it converges absolutely for all x in E, and E complement is, measure of E complement is 0. Now we want to show f is in L1 mu. Okay. Now we know that if Gn is plus Fn, no, not recalling, I'm just writing my Gn like this, only the, it's like the sequence of partial sums of these functions. Okay, is that correct? We have shown this.
Yes.
Therefore, by Libate Terminated Convergence Theorem, we can bring the limit inside. That's just and what's this? What is Gn? Gn is this F1, F2, Fn. So I write K going from Fk d mu. And this is a finite sum. There are a finite number of functions. So we have said the integral is linear. So this is just right? You get this? And that's okay. Let me just cheat a bit, which means okay. Sorry. Okay, going from 1 to n and going to infinity. Now this is okay. And this is summation. But we know that E complement has measure 0. And we know that on sets of measure 0, the integral makes no difference. So I could write just this. We have seen this, right? Okay.
Okay.
So what we did was we brought everything down to the subset on which things were actually defined outside the set. Outside that set, the measure was 0. Prove everything for that subset. And then, because you know, this step we did already, like I keep saying, sets, negligible sets make no difference to the integral. So E complement does not matter. So we write come from here to here. Okay. So this is a homework. Prove the following version of Libate dominated community. And often you will use it in this form. So you have fn's measurable on x. You know mod fn x is less than equal to gx almost everywhere on x, and limit for almost all x belonging to x. Then f belongs to fx L1 mu and okay. So this same idea will work. You'll have to reduce to a set of measures, to a subset, E maybe, prove everything for that. So you will come to the final equality, but instead of x, you will have an E. And then that's the same as integral over x. So it's not really very difficult to do, but a good exercise in how to maneuver such conditions. Okay? Whew, that took longer than I thought it should. Okay, so last few results about almost everywhere ideas. So suppose if from so that's the first one I want to prove. What can you conclude from here?
F equal to 0 almost everywhere.
Almost everywhere on E. If can I just start proving it one by one instead of having to go back and forth? So I'll just prove this and then write B also. I think there won't be any harm in doing that. Okay, how do we prove this? So you're given that integral of f over the set E is 0. And we want to prove that f is 0 almost everywhere on E. Okay. So f is a non-negative function. So first thing we can observe is that I could break E as, so basically I want to show the set X this set should have what measure?
0.
Exactly. So I want to show this set has measure 0. But observe, I could write this set as the union of this is a standard trick. Yeah, we could do that.
Yes, ma'am.
And so if I can show that each of these subsets has measure 0, we are done.
Yes.
Okay, so let me call this one. And let us call out this subset. Okay, then what can you say about this is going to be less than f d mu, because on A and f is greater than or equal to is greater than 1 by n. Yes, and f is a non-negative function, so this can be right.
Yes. And that is
this
0.
is and what is this extreme left-hand side?
That is also 0.
Hmm?
Integral
1 by n mu of a n.
equal to 0.
So this implies mu an is 0, right? And true for each n. Therefore, by 1, mu of the set X belonging to E is 0, right?
Yes.
And what does that mean? F is 0
0 almost
almost
everywhere.
everywhere on E. Okay, so the B statement says,
Hello, ma'am.
yes,
If we will remove non-negativity condition, that then we cannot. If we will remove non-negativity
Yes,
condition,
absolutely. See, look at the statement A. F is from x to 0 infinity. F cannot be negative. Okay. Now suppose F is Lebesgue integrable. And this the integral of F over every measurable set is 0. What do you think the conclusion should be? Now I am not saying, so that was the first step, it was non-negative. Now I have removed the non-negativity condition, as somebody just mentioned. Then okay. But we have already shown something for non-negative functions, and now we want to say, of course, this is a much stronger condition. You're saying over every e, the integral is 0. And how do we prove this?
F plus
Any
function
idea?
and F minus function is
Yes.
almost everywhere.
So we can write F as this. F is this, and by definition, we defined it, remember? What is this? 0 is this. Integral is this u plus, and so on, right? All of these terms. And individually, each of the integrals on the right-hand side is what? Is the integral of a non-negative function. So if I can choose E in the correct manner successively, I will be able to show each of these u plus u minus v plus v minus are 0, isn't it? So can you guess what? So suppose I want to show u plus is this integral u plus d mu e is 0. What should E be? So first, let E be this number x. Then u is u plus, of course, right? And I don't know what to call this. I'm calling it 1. So then by 1, so this 1 is for every E, for every E. Now I have chosen E to be a particular set. What will we get? Right?
Okay.
So this implies by A, u plus is 0. Yes?
Yes.
But E is what? That means u plus is 0 on this set. So similarly, can I prove u minus V minus, V plus and all that? Yes?
Yes, ma'am.
And what will we get? Similarly, choose second round, you choose E to be X such that Ux is less than 0 and so on. We get U minus is 0 and so on. V plus, V minus 0. Similar manner. Okay? So
Okay.
putting all of this together, we will have that F is 0.
Almost everywhere.
Okay? And the last one, I want to do the property that, remember we showed, okay, let me just write down the formal statement. If F belongs to L1 mu, so what can you say about this? We had proven this property the first lecture maybe, or this. What is this true? What can you say about this? We know this is less than.
Mod F.
Integral of modulus of
D.
FT.
Okay, so now this statement is saying that this will become equal. Then there exists a constant alpha such that alpha F is mod F almost everywhere on X. Okay. So in effect, this statement is telling you when will equality hold for the usual inequality we have. We always have this inequality for Lebesgue integrable functions. This is over X, of course. If you want equality, you know there must be an element, a scalar alpha, such that alpha F is mod F almost everywhere on X. Okay. So to prove this, I'll take you back a little bit to the proof we did for less than equal to. How did we prove this?
Hello.
Yeah?
Ma'am, in last proof, if we will add function is non-negative, then we can say this theorem hold for if and only result.
Sorry?
If
No, that we've already done, no? If the function is non-negative, then you don't need the full power of all the hypotheses of B.
no, ma'am.
You see?
I am talking about if and only if result.
For?
If and only if result converts part.
Yes. For which one?
In last proof. I think A part.
C. A part.
Yes.
Yes. What about it?
Ma'am, I am saying this means forward part is true. Whatever
Yes,
you are done.
Yes.
If we will add function is non-negative, then we can, what about say converse part?
Now, if F is 0 almost everywhere on E,
Yes.
then always the integral over it will be 0, no?
Yes, ma'am. So that means this theorem is result for means converse part also.
That is trivially, we have seen this so much, several times. I mean, I want to stress this again, in fact, because you have brought it up. Almost everywhere on E means F is 0 on some subset of E, and outside that subset of E, the measure is 0. Okay? So when you write this integral here, you can write it as E, it's X. So X, so it will be E intersection F maybe plus intersection plus F complement. Okay, so F is that subset of E where this function is not 0 maybe, but that measure is 0. So it will contribute nothing to this measure, this integral. All right.
Yes, ma'am.
So it is trivially true. There is no question of non-negative or anything here. Okay.
Okay.
Can I go back to C now? Right. So do we have time?
Time is up.
Okay, so I will stop here and this is homework. So what hint? Go back to the proof. The inequality. So you revisit that and use what is given, the equality, and I think you should be able to prove it. Okay. So I will stop here. And from next, I will start with a new topic next time. So these are the basic tools that you will need in working with the integrals. Okay, so thank you. I'm sorry I'm a bit over time. I will stop sharing.